All right, hello everybody. My name is Stephen Hummel. Welcome to tonight's live deep sky tour, where I'm going to be showing you some faint and fuzzy things you can see in the sky right now, far beyond the reaches of our solar system. Actually, except for one thing within our solar system. But I'm located at McDonald Observatory. We are a research facility of the University of Texas at Austin, and we are located in the far West Texas desert, up in the mountains. We're actually the highest point you can drive to in the state of Texas, and a beautiful location. Here pictured in the rain with a little rainbow there, but usually it's not raining. Tonight it's a fantastically clear night, perfect weather for this kind of a program. I honestly couldn't ask for any better conditions. But I am not located up there with our research telescopes. I'm located down at our visitor center, where we have several other telescopes. Now, at the moment, McDonald Observatory is closed to the public, so you can't come visit us for the near future at least. However, we are still doing research with some of our larger telescopes. But when we do eventually reopen, whenever that is, we would like you to come on down and have a visit. And if you do come and visit us, we highly recommend you come to one of our star parties. We get to look through one of the telescopes down here at our visitor center. And I'm located at the one with the arrow in there. So the telescope I'm going to be using tonight to show you the sky is located just behind me. And of course, it's very dark in here. I only have red lights on, and the video is kind of grainy because it's very dark, and that's really crucial to this program working. In fact, the camera makes it look a lot brighter inside here than it actually is. I can't see that moon picture behind me. Uh, that darkness is really critical to the kind of work we do here at McDonald Observatory, because we're trying to study some very faint things in the sky. And McDonald Observatory is located under some of the darkest skies in the continental U.S., and that is really one of the main reasons why we're successful. Also, the abundance of clear skies helps too. But this week is actually International Dark Skies Week, so you picked a good night to come view this program if you didn't know that. And if you're curious about how you can help keep the skies dark, not only here but where you are, you can go to our website, mcdonaldobservatory.org, and under the Learn tab, you can learn about our Dark Skies initiative. Before I get too carried away with this program, I do want to add that if you have any questions for me or just about astronomy in general, if you're logged into YouTube, you can ask questions in the live chat. I have a team of moderators helping me out, monitoring that chat, and they will be able to answer most of your questions. But if we think it's a particularly interesting or good question, or something that only I can answer, or something like that, or it can't be just typed up in that kind of a format, only 200 characters on there, then those moderators will forward your questions to me towards the end, and I'll take more. And even then, I probably still can't get to everyone. We've been a little overwhelmed by questions lately. So if you look at the description for this video, you'll see that there's a link where you can submit another question which we could follow up on later in a dedicated video. So if we don't get around to answering your questions through the course of this program, I encourage you to submit your question in the link in the description. All right, so again, I'm going to be showing you some things, and I have a camera attached to the telescope. It's always important to note that a camera does not work like our eyes do. Our eyes at night are very sensitive, but they don't really see very well in color. And so the camera I'm using is not going to be color because this is supposed to kind of roughly approximate what the object actually looks like through an eyepiece, as opposed to many hours of exposures bringing out lots of color and things in some of the pictures you've seen online. That's not to say the objects we're looking at are devoid of color, however. We just did that because we think it'll better approximate what it really looks like. And as it turns out, monochrome or black and white cameras are a lot more sensitive, so you get a better quality image compared to a color camera. All right, but our first target tonight is known as M53, Messier 53, and it is located kind of low right now over in the east. And so we're looking eastward here. So this line stretching above us is the middle point of the sky. So we're looking kind of east. And M53, or Messier 53, is a globular cluster, which means it's a gigantic ball of ancient stars. And here is what that looks like live from the telescope right now. Again, I've got a big globular cluster. So what that means is a giant sphere of stars, and if you watch the previous ones, then you saw another different example of this kind of a thing, which the previous one we looked at in our first broadcast was M3, but this is M53. And globular clusters like this are all, generally speaking, enormous balls of thousands of stars in one giant sphere. And they're, generally speaking, very old, billions of years old. Our Milky Way contains roughly 150 of these kinds of objects. And again, if you look on the top right up here, you can see how that the image is refreshing. So this is a live view. And it would kind of resemble that in an amateur telescope, a nice telescope. It would be a big ball of lots of little stars really packed in there. So there's a lot of stars very close to each other. Now I'm going to start improving the picture here by adding more frames on top of it. And what that's going to do is it's going to bring out fainter details that and hopefully give us a better quality image over time. But it's going to take a while for that to really go into effect. But I have a visual here that kind of talks a little bit more about what a globular cluster like this one really is, here from data from the Hubble Space Telescope. A lot of stars packed in very close. Again, in the case of the globular cluster we're looking at, it has over 100,000 stars in an area under 100 light years across. But here, zooming in on this globular cluster, this is data taken from a different one, but it's pretty similar. We got lots of stars. When a lot of amateur astronomers talk about objects like this, they make them sound like they're these giant ancient balls of stars that aren't really doing anything. But the stars are actually moving around. Here in this animation, you can see that they're kind of chaotically orbiting around each other. It's very complicated. They're all their orbits down in the center. It's very hard to keep track of there. So there's a lot going on in these globular clusters, all these stars orbiting around each other, and gravity is keeping all these stars together into one giant ancient ball. So this object, again, is many billions of years old, maybe 12 billion years old, and it's located 58,000 light years away, 58,000 years for the light from this object to reach us, again, at the speed of light. So 1 light year, if you're not familiar, is not a unit of time, it's a unit of distance. 1 light year is 5.88 trillion miles. That's the distance light travels in 1 year. Let's bring out a little more detail. Stretching the image, you can see that there's a lot of stars in the center and they gently trail off. Now, gravity is generally keeping these stars in one group, but that's not to say that it can't lose stars. Sometimes, as the stars orbit around each other in these tight, rapid orbits, one of them will get flung off. If it picks up enough speed, it'll just be flung off. And so these clusters actually do lose stars very slowly over many millions of years. But again, this object is called Messier 53. And Charles Messier, who documented this object in 1777, was a French comet hunter. Again, he was looking for comets from Paris, and you could do that from Paris in 1777, back when light pollution wasn't nearly as much of an issue as it is today. But in his little telescope, a comet looks like a big kind of fuzzy, hazy ball. And that's kind of what this looks like too. Of our telescope, we can see that it's stars, but you can kind of imagine that if this wasn't such a good image, you kind of fuzzed it up, it would just be this kind of hazy glow. And that is what a comet looks like. Really, comets are just kind of big, fuzzy, hazy glows. But he knew that this particular thing couldn't be a comet because it just stays put relative to the other stars in the background. So it can't be a comet. But we're going to look at a real comet next. This next object is a comet that's in the sky right now. We're going to slew over there, so you'll see the telescope moving behind me. It's located in the north. I'm going to start moving the dome around. Now, it's still kind of deep twilight right now, so hopefully our view of this will be all right. It's not 100% dark just yet. Takes a while for the dome to catch up. But yeah, this object is located in the constellation of Camelopardalis, which is kind of an obscure constellation, but it's known as the giraffe constellation. Camelopardalis is basically a giraffe in fancy speak. All right. So I'll show you my map of the sky here again real fast. All right, so that's where we're aimed right now. That's the North Star right there. So we're looking kind of low in the north at the moment. It's relatively low. And this comet is perhaps not the comet you think it is. If you've heard in the news that there are comets in the sky, well, we're not actually looking at the same one. So give me a quick moment here to get this set up. Yeah, there we go. All right, so here's our view right now. So you see that little fuzzy thing? That's a comet. This is Comet C 2017, the year it was discovered, T2 PANSTARRS. So 2017, the year it was discovered, T2 kind of just a random a designation going through a series of other designations. And PANSTARRS being the name of the telescope that discovered it, or the observatory. That PANSTARRS is in Hawaii. They're actually one of the very few other observatories in the world right now that's still doing research. It's us, PANSTARRS, and just a handful of others. But you see, that fuzzy core there, that is the bright nucleus of the comet. And you can kind of see it has a faint halo stretching around it. This is roughly what it looks like in a telescope right now. You can see the center, but not so much the comet's tail. Now, to quote David Levy, famous for amateur astronomer, discoverer of many comets, comets are like cats. They have tails and they do what they want. So that's to say comets can be kind of fickle. This one does have a tail, however, it's very faint, and because it's not 100% dark just yet, we're gonna struggle to pull it out. But I'm going to start combining exposures, and we're going to see the quality of the view here improve over time. As we watch, we should see the more details slowly being pulled out, although it'll take a while. While we're waiting for our view to improve, I have a little animation to explain kind of what it is, what a comet really is. So comets are objects within our solar system that are orbiting the sun, but their orbits don't take them on nice circles like the planets. Usually they come from far out in the outer reaches of our solar system, and then something nudges them, and then gravity takes over and it draws them in towards the sun. And as they fall towards the sun, they heat up a bit, and the ice and other volatile compounds that make up the comet evaporates, and that's what causes the glow we see. So here in this animation, you can see there are lots of comets out there. A lot of them actually just fall towards the sun and burn up, and we never see them again. And some of them break up as they're approaching the sun, and so they break up into smaller chunks. Actually, a lot of meteor showers are caused by broken up debris from comets still kind of going around the sun, but just tiny little bits of debris. And when they hit the Earth, they burn up in the atmosphere, and that's what forms a meteor. So again, don't confuse those two things, meteor and comet. A comet is something out there in deep space. A meteor is burning up in the atmosphere. A lot of people often get those two things confused. Now, I don't have a lot of data on the particular comet we're looking at tonight, other than the fact that it's about 160 million miles away from us. But these images here, these were taken by the Rosetta spacecraft, and this is Comet 67P. I'm not going to try to pronounce the rest, it's really complicated, but 67P, let's call it that. And this is a somewhat typical comet. We've actually landed something on it. And so comets are like giant dirty snowballs. They're mostly made of literally dirt, basically, and ice. Water ice, as well as other ices like carbon monoxide and dioxide and other things. And as they approach the sun heats them up, and then the ice sublimates. It turns to gas, and that's what gives off everything. So the core, the nucleus of the comet, like we see here, is relatively small. And the comet we're seeing in this picture, it's only about 2.5 miles across. We don't have good data on exactly how big the comet is that we're looking at right now, other than that it's probably about a few hundred to a few thousand feet across. All right, so again, we can see that this is the comet right here, and now that we've lengthened the exposure a bit, you can kind of see that it is sort of trailing off down below. It's faint. We'll try to add some more contrast here. Yeah, kind of down below. You can see that there is a sort of a tail to it. And so that tail is pointed away from the sun. So as the comet goes around, the tail will tend to point in the opposite direction from the sun. So the solar wind, the stream of particles, is pushing that tail back and sculpting it. Now, again, this is Comet 2017 T2 PANSTARRS. Some other comets made the news lately. Comet 2019 Y4 Atlas was recently in the news a lot as a potentially very bright, almost naked eye comet. And I would look at that, except for the fact that it broke apart. Here's some images I took with the setup we're looking through earlier this month. This other comet, you can see it started out on April 8th as a little point of light, and then on April 11th, it kind of smeared out. And if you look down at April 13th, it's almost two brighter chunks. It actually broke up into smaller sections. So again, comets are fragile, and as they heat up, they tend to break apart into smaller chunks. So this comet, the pictured here, which was in the news a lot, is no longer really all that interesting to look at. It's basically faded away. Again, they do what they want. They're very unpredictable sometimes. However, although this one broke apart, the one we're looking at tonight is somewhat stable. It's been around the sun more than once, and usually a lot of comets don't make it their first trip around the sun. They burn up. But if they survive that, then they can survive to go around many times more, and that's the case with this one. It's probably going to stick around with us for a while. All right, so but it is our kind of guest for the evening. It's not. It will move. If we were to come back in an hour or so, it would have moved from here to say over here or something. So they do drift across the sky very slowly, although we're not going to see it move very quickly in the short time we're going to spend with it. But it won't stay where it is for very long. Okay. All right, so again, this is our guest star for the evening, I guess. I think it's pretty good. Now that we've lengthened the exposure, actually, you can see there's another little background galaxy up here in the back. Just also happens to be in the field of view. All right, so next up, we're going to look at a galaxy. And this is one of my favorite galaxies. It's a big spiral galaxy known as M101, Messier 101, also known as the Pinwheel Galaxy. Start moving the telescope. And start moving the dome as well. This object is also within Ursa Major, or actually pretty close to the tail end of the Big Dipper, as most people know it. All right, and here it is on my star chart here. So there's the Big Dipper, and just below it down here is M101, the Pinwheel Galaxy. And just give me a moment there to get it all set up for you, get a nice pretty picture going. All right, so this is a very large spiral galaxy, and let me do some things here to improve our image quality before I send it over to you. All right, so it is located about over 21 million light years away. 21 million years for the light from this galaxy to reach us. All right, here we go. And you can see that this is sort of what it looks like in the telescope. We've got a brighter center to the galaxy and very faint spiral arms kind of branching off. But they are quite faint. So at first, they can be kind of hard to pick up, especially in an amateur telescope. You can see it, but it is actually a more challenging one because its light is so spread around. But again, over 20 million years for the light from this galaxy to reach us. It's an enormous spiral galaxy, over 170,000 light years across, which is really enormous, absolutely huge. All right, so now we're going to start adding more exposures here. We're going to bring out more detail as we go along. And let's start with a longer exposure. Let's go for 15 seconds or so. There we go. Yeah, so now you can see its spiral structure a little better. So again, that's a rotating galaxy, and the spirals are very spread out in this one. And galaxies generally have sort of flat disk shapes because if you start out with a big clump of material that's all going every which way, and then you give it enough time, gravity will want to make it contract so long to a disk if it's especially spinning. Just like imagine you have a ball of dough and you want to make a pizza. Instead of trying to flatten the dough out, if your chef is trying to make a pizza, they start with a ball of dough, they throw it in the air, and they give it just a little bit of spin. And that spin flattens the ball out into a disk. And that's why we tend to see that pattern a lot in space. Galaxies tend to be disk-shaped. The rings of Saturn, the planets in the solar system, they all follow that similar pattern for that reason. All right, so now that we're bringing out this detail, you can see that there are these specks within the spiral arms going around. This one here, got another one over here. These are star-forming regions. So those regions, those clumps, are an indication that this galaxy is alive and well, that it is actively forming new stars. If you're with us for our first deep sky tour, we were looking at the Orion Nebula, the first thing we looked at. That's a big star-forming region within our galaxy. Gas and dust is coming together and forming new stars, and those bright young baby stars shine with a lot of heat and energy, illuminating the cloud around it. That's exactly what we're seeing here in this galaxy over 20 million light years away. And there's a lot of star formation going on in this galaxy, especially within the arms. Because as the material goes around, it's clumping up in the arms, the gas is coming together and forming new stars. But the gas has to not only come together, it has to be relatively cold in order for new stars to form. So galaxies eventually run out of hydrogen and cold gas from which to form new stars. So this period in the galaxy's history, in cosmological terms, is relatively short. It only rapidly forms stars for a little while. It's the equivalent of flooring the gas pedal. You may form a lot of stars relatively quickly, but it can't keep that pace up for very long. Another interesting fact about this galaxy is it's very, very large in terms of diameter. Again, over 170,000 light years across. It doesn't even actually fit into my field of view here. For reference, our own Milky Way is 100,000 light years across for its main section. Again, this is 170,000, so it's very large, but also very spread out. It's not as dense as some other galaxies. Well, I think that's just a magnificent image there. I don't know about you, but I love seeing spiral galaxies face on like that. But the next object we're going to look at is another spiral galaxy. However, well, actually, there's debate about whether or not it's truly a spiral galaxy or not. But again, this was the Pinwheel galaxy, M101. And I'm gonna stop the exposure there. The next galaxy we're going to look at in our tour here is known as the Sombrero Galaxy. And it's also M104. And this is going to be a little bit of a larger move to get to it. You can see the telescope moving behind me. Start the dome moving around as well. You'll see why we call this one the Sombrero. I think it'll be pretty obvious. All right, and here we is our map. It is located kind of low in the southeast at the moment, near the between the constellations of Virgo and Corvus, the Crow here. And so give me a quick moment to get it set up just like before. And let's see here. All right. Get a There we go. All right, so here is our view of the Sombrero Galaxy. And the sombrero at the moment is upside down, I have to say. You know, there is really no up and down in space. Things are oriented every which way. But you know, the idea is that this bright part is the top of the hat, and the dark line is the brim of the hat of the sombrero. So the Sombrero Galaxy is over 30 million light years away. So again, it took 30 million years for the light to reach us, and it generally resembles that in a telescope, in a high-powered telescope. It does look like that. It's got a very bright center, almost star-like core to it, and then this dark line of dust and gas. So the galaxy looked at before was face-on. Now we're viewing this one more edge-on. But let's take a longer exposure. Let's start stacking the exposures together. Let me clear that out there. And we'll start to see more detail pop out here pretty soon. Okay, so what's really going on here is that this is a galaxy that has merged together with other galaxies. And the way we know that is from several clues. The first is that there are no big, bright star-forming regions like we saw in the Pinwheel galaxy in this one, the Sombrero. There's no clumps within the disk of the galaxy, which tells us that it doesn't have a lot of cold gas just sitting around to form new stars. It's basically what we call red and dead. It's used up all of its fuel to form new stars, and all that's left are older, more fuel-efficient stars. So if you were to look through this with superhuman vision and see it in color, you would see it's kind of a yellowish, orangey color. Not a lot of blues in there from very hot young stars. But you can kind of make out that there is this line of dust in here, and that it's got some texture to it as well. And so there is starlight kind of seeping through this line of dust and gas within the galaxy. But when galaxies merge together, usually they form lots of new stars really fast, run out of fuel, and no new stars form anymore. So the lack of new star formation could be an indication that this galaxy merged with other ones. The other clue is that it has a very faint halo around it, right? So it's not all just a disk. There's kind of a fainter glow around it. And so something probably disturbed the orbits of these stars and kind of scattered them around, and now they're kind of orbiting in a general halo instead of along with the disk. Another interesting clue that behind the history of this galaxy is the very bright center. Now, last week we saw M87, an enormous elliptical galaxy, which was definitely the result of many, many, many galaxies merging together. And that galaxy had a very massive black hole in its center, and a jet coming out the side. This galaxy has a black hole as well, and although it may not have a jet, it is a very active black hole, and the area around it's very hot. We call it an active galactic nucleus, and that's why the center is so much brighter than everything else. We think there's an active black hole consuming material near the center, which is heating up the area immediately around the black hole and emitting lots of light, and that's what we're seeing. This black hole is unusually large compared to the mass of the galaxy. This galaxy is 50,000 light years in diameter, which is half the diameter of our Milky Way. But in terms of mass, it's almost the same size as the Milky Way. Our Milky Way has got a black hole, and it's the center of it. We don't have to worry about it. The Milky Way's central black hole is about 4 million times the mass of the Sun. That sounds like a lot. 4 million suns worth of mass in one object. This galaxy, despite not being all that much different in terms of size from the Milky Way in terms of mass, its central black hole is over a billion solar masses. So it's way bigger for its size than we would expect. That's very strange. That the black hole at the center that's making it so bright and immediately around it is kind of outsized compared to the size of the galaxy. And we think that could be a result of other small objects, like maybe even other black holes merging together many billions of years ago to get it to be that big. It's definitely an object of further study, though. This is a very interesting galaxy that I think we still have more to learn from. All right, and yeah, now that the exposure has been going on for a while, you can start to pick out some background galaxies here, like this one, and some other faint. If you see a faint fuzzy thing in the background, that's probably another galaxy, many, probably hundreds of millions of light years away, and it just happens to be kind of behind the galaxy we're looking at. So a little more contrast. Let's zoom in again. I just like the detail within the dust lane here. You can kind of see that it's not just a plain old line. There is actually some texture from the clouds of dust and gas within that. All right, so again, that's the Sombrero Galaxy. And the next, our last object for tonight is a lot closer to home. Not as close as that comet, but it is known as the Ghost of Jupiter. Ghost of Jupiter, which is kind of a silly name. It's a cool name. I think it sounds awesome. But you know, I think we could probably come up with better as well. I have issues with a lot of the nicknames of these objects. All right, not too far away from where we were looking. This object is in the constellation of Hydra. And it's low and straight south at the moment. So I'll flip back to my map for you. All right, and looking at the map, you can see that this line here, this is the middle point of the sky, the meridian. You don't have to worry about that. But it is very close to the middle point of the sky, directly south right now, within the constellation of Hydra. All right, and give me a moment again to get this one set up. Okie dokie. This is a bright object. This is only 1.2 seconds of exposure, and it's already pretty clearly there. So this is let me adjust the settings here to try to make it kind of match what it actually looks like in the telescope. It looks a bit like that in a telescope. Very small, but with lots of detail. So this is another planetary nebula. Planetary nebula meaning it is a shell of gas that is expanded off of a star that was once similar to our sun. And I've got this animation. I love this animation. It just kind of summarizes it. When stars like our sun age, they puff up and expand and blow off their outer layers into this halo around them, this cloud of gas and dust. And the heat of the dying star makes that cloud glow, and that's what's causing what we're seeing. Again, we call this kind of a thing a planetary nebula. Now, I talked about two other planetary nebulas in the last two episodes, but what I didn't really talk about is what happens exactly to that star at the center. So again, objects like this are formed when stars around the mass of the sun, in this case maybe a little bigger, run out of fuel. They puff up, they form a red giant, and then they blow away their outer layers into space. But although the outer layers are left, about half the mass of the star or so collapses inward to form what's known as a white dwarf. And white dwarfs, you could debate whether or not they're actually stars, because by some definitions, a star has to have nuclear fusion at the center, generating heat and energy and making it glow. A white dwarf doesn't have that. They're about maybe around the 70% the mass of the sun or so on average, compressed down into an area the size of the Earth, which is incredibly small for a star, very compact. But there's no fusion going on at the center. It's only glowing very hot from the heat of being so dense and from being inside of a star for billions of years. Let's increase the exposure here and bring out some more. You can see that it is actually so bright, it almost overwhelms the sensor there. So the star in the center is a white dwarf now. It's a star that has basically died. It's retired, I guess, would be a better way to say it. It's a retired star. And the heat of that little retired star is making the gas around it glow. Now, this isn't a color camera, but if it were a color camera, this would be a very obvious blue-green color. You could see the color in this object. Our eyes are most sensitive to blue and green at night, and least sensitive to red. That's why I'm using red. It takes a lot of light. It has to be pretty bright to activate the color receptors in our eye, but this object is bright enough to do that. It is bright enough to activate the color receptors in a small telescope, and so this is a greenish cloud. And actually, it's green because of the presence of oxygen generated late in that star's life. And this layer of oxygen was pushed off away from the star, and then it's glowing. It's ionized to make it glow this green, blue, or teal color very strongly. So if you look up pictures of this, you will see it as that distinct color. All right, so again, it's called the ghost of Jupiter because, well, it's kind of the same apparent size as Jupiter in the sky, and that's about it, really. I don't really think it looks like Jupiter very much, but that's the case with a lot of these things that their names, they require some imagination. All right, so this is the last object on our list to observe tonight. However, if you've got any questions for me, I'll be happy to take them, and you can send them in the chat, and the moderators will send them to me. And I do want to add that if you enjoy these programs, we will be doing more of these in the future, and you can see the dates on our social media, our Facebook, our Twitter, or Instagram, and you can also subscribe to this YouTube channel. And if you want to support us, we are a nonprofit organization. There's a link in the description below on how you can help support our education and outreach efforts. All right, but I'm going to start trying to answer as many of these questions as I can get through tonight in a reasonable time frame. All right, so Jeremiah Paredes asks, what is a comet's tail? What is a tail? Well, basically, the tail of a comet is evaporated material, basically water vapor or things of that nature. Sometimes other things like carbon monoxide and carbon dioxide. So they're in a comet, they're ice, and then the heat of the sun basically turns them into a gas, and so that stream you see coming off is for the most part things like water vapor and other vaporized ices. And they could be very, very long, millions of miles long, but very thin. You could fly through that and never really know that that's what you're doing. There's not a lot of stuff there. It's very, very thin material floating through space. Another question, John Sotera, do they have two tails? Yes. So some comets can have more than one tail. And usually, and some don't have any tails. So there's kind of a area in a comet's orbit around the sun where the heat is enough to melt the ices, and the pressure of what's called the solar wind is enough to sweep them back. But if it gets too close, then actually the tail doesn't even have a chance to form. Basically, the material just turns to gas so fast that there's really nothing to even form a tail, or just disintegrates. But there's a kind of a sweet spot, and so some of the material may have kind of fallen off, just a fine grain of dust and material. Microphone keeps wanting to cut out on me, but sometimes that forms a tail along the trajectory on which it's traveling through space, just leaving a trail of debris, and then a second tail can be, say, on the opposite direction of the sun. So one from along its path of travel and a one opposite of the sun. And in fact, sometimes they can have multiple tails, spokes even, if depending on the stream of material coming off the sun through space, sometimes can create interesting patterns. It can have multiple spokes sometimes. Robert Weedy asks that how do we know that globular clusters are some of the oldest structures in our galaxy? Basically, we know this because of the kinds of stars that are found in these clusters. The bigger the star, the faster it burns out and dies. And so big stars don't live long. And so we don't find very many big stars in these globular clusters. For the most part, they're relatively smaller, more fuel-efficient stars, smaller than our sun. The smaller stars can live many billions of years. Another way we know that is because of what we call the metallicity of the stars. In the early universe, almost everything after the Big Bang, all there really was for a while was hydrogen and helium. That was basically it. And these clouds of hydrogen and a little bit of helium came together. They became dense enough to form stars. And the process of fusion inside those stars fused the hydrogen into other elements. Then the star died, spewed its content out, and then the stuff got recycled. So basically, the very first stars in the universe, therefore, couldn't have all that much material like carbon or iron or gold or uranium in them. And they would basically be mostly made from hydrogen and helium and trace amounts of other things. And so astronomers call anything other than hydrogen and helium a metal, just to annoy the chemists. We call that a metal. Again, carbon to astronomer is a metal, and so on. Oxygen is a metal. So we look at the abundance of all those things that are not hydrogen and helium in these stars. By breaking the light apart into its spectrum, this method called spectroscopy, we can learn what stars are made out of. And that's how we know that these stars must be very old, because of their very low metallicities, their low abundance of other things. All right. Let's see what other questions we got. He asked another question. Why does the Kuiper Belt orbit in the same plane as the planets, but the Oort cloud is 360 degrees around the solar system? Is this just a distance kind of thing? So our solar system is generally a disk, and the Kuiper Belt is a ring of objects basically in line with the disk, and the Oort cloud is this kind of big spherical thing. It is mostly a distance thing, most likely. The further you go from the sun and the inner planets, the less you're going to feel the gravitational effect of all of that. And so there's a lot less force acting on the Oort cloud way far away to try to make it come down into line with the rest of the solar system. The Oort cloud is very far out, away from the sun, so it doesn't feel those effects very strongly. David Humphreys asks, what software am I using for my camera? The software is SharpCap. SharpCap it's actually free. Is the software. Robert Wheat asks another question. Is the idea that supermassive black holes in the middle of galaxies the primary driver for the rotation of the galaxy? Not necessarily. The rotation of the galaxy may not have all that much to do with the black hole at the center. In other words, if you were to remove the black hole, things would still be going around in a circle. Black holes are actually not that big in comparison to the whole galaxy. Most of the mass of a galaxy is found in stars and gas, not in a black hole. Black holes are very dense, but in terms of a fraction of the entire galaxy, they're really not. We think they're basically it's just their momentum and what I kind of described before, the collapsing down into a disk that's making it rotate. And the black hole isn't necessarily isn't necessary for that to arise, although it may play a small role in the overall evolution of the galaxy. All right. Have you noticed any lessening in light pollution during this time? It comes from Anna Rader. That's a good question. I've been asked a lot. I've been really curious. Now that we're in a shutdown, right? You would think that people were turning their lights off and such. Nope. We've taken some data and kind of preliminary things. And it looks like the skies are basically the same as they were a few months ago before everything shut down. We're kind of in the middle of nowhere. And yes, the oil and gas industry to our north is experiencing a huge tumult and lots of things are shutting down. But just because a business is shutting down doesn't mean they're turning their lights off. Usually, what it means is the bank takes over their property, and the bank wants to keep the lights on for safety. So we don't really notice that much of a difference in terms of sky quality during this time. They're still good, basically. They're just as good as they were before. Let's put it that way. All right. Question from Jennifer Jackson. Has the decrease in Earth pollution changed the way you see space objects? So I was at the previous question I was talking about light pollution, right? Artificial lights. Now out here where we are, we're not near any major cities, so we don't notice air pollution very much. So I don't think I don't really think that this whole shutdown has had an effect on the quality of our skies very much. However, in other areas, say observatories near cities, I'm willing to bet that yeah, say observatories near San Diego and LA, such as Palomar Observatory and Mount Wilson, and others there, they probably have clearer skies a bit because of less air pollution from less people traveling around. All right, a question from Michael Weinstein, I don't know. Stephen is so knowledgeable and entertaining. Oh, thank you. Perhaps he could describe his educational and professional background and how he came to be our Star Tour guide. I appreciate that, Michael. Well, I basically just started off as an amateur astronomer, and shout out to some of the people I know who are watching this who actually I learned from the Astronomical Society of Eastern Missouri. And I was just basically, I was in college. I thought astronomy was really cool, and I bought a telescope and just got into astronomy, and I learned a lot from basically just looking up at the sky and teaching myself, as well as learning from other amateur astronomers. And then I got a job here, and I started taking astronomy more seriously and reading up about it more. And also just the fact that I'm here at McDonald Observatory is a tremendous opportunity. I mean, there's so many brilliant people around me. Well, not right now. I know they're out there, but I haven't actually been near them. But I've just absorbed, I guess, so much information just from working here. But I don't actually have a degree in astronomy. My background is actually in economics, international relations, and I just kind of caught up on astronomy later on, kind of during and through college and later. All right. Let's see, another question. Okay, I'll just take two more here. This is from Destination Discovery ASMR. What is the best book that you would recommend for a 13-year-old who loves space? Ooh, Astronomy for People in a Hurry by Neil deGrasse Tyson is pretty good. That's a good one. If you want to learn more about what's in the sky and how to observe things with a telescope, then I recommend Turn Left at Orion. That's a very famous guide to the sky and how to use a telescope. And it kind of depends what you're looking for. If you want the theory, there are books for that. And if you want just to observe with your own eye, there are books for that as well. I recommend doing what I did and buying a telescope, seeing these things for yourself, and getting inspired to learn more. That way, when you learn about something, if you've already seen it with your own eye, you can kind of put it into context and think, oh, this is really real. This isn't just some abstract thing. So I recommend Turn Left at Orion to really get the spark going, and then again, Astrophysics for People in a Hurry by Neil deGrasse Tyson for the more theory related stuff. All right, this will be my last question. We're kind of out of time. Again, we can take more questions if the moderators can't get to you in the description. There's a link where you can submit more detailed questions, as well as to specific people. All right. Paige Bauer asks, my son, Gus, who is 8 and watching, would like to know how many galaxies exist. Ooh, if we could count all the galaxies. To quote Carl Sagan, something he never actually said, billions and billions. Basically, wherever you point a telescope, you'll see a galaxy. There are perhaps over 2 trillion galaxies in the observable part of the universe. And they're just absolutely everywhere, and that's just a part of the universe that we can observe. There's more beyond that. Again, trillions of galaxies. Each one of those galaxies has billions of stars on average, and we think most stars have planets going around them. So like at least one or two on average, perhaps more, as we learn more about how the planets form. So there are just untold trillions and trillions and trillions of worlds out there waiting to be explored, waiting for us to discover them. And that's a relatively new field, finding planets orbiting other stars. But yeah, the universe it is big. It's an understatement, but it's really really big. So we're never going to be done learning about it. All right, this has been a wonderful evening. Thank you all for joining me. Again, we'll do more of these in the future. And thank you to my moderators for helping out. I also want to add that I'm not going to be the only host for these programs. I kind of got this started, but other people are going to be hosting this as well, so I don't want to steal the spotlight. But pretty soon we're going to start doing programs about the moon as well as the sun. So we've been doing these programs because the moon hasn't been up, which means the skies are dark and we can see these faint things. When the moon's in the sky, we'll be focusing on that. It'll be my friend Kevin Mace, is going to be hosting those programs too. Again, thank you again for joining me on this program. I love looking up as always, so this is just a lot of fun for me. Y'all take care and clear skies, everybody.